Hello, and welcome to a short introduction on our paper on improving GNSS positioning using neural network-based corrections. Deep neural networks are promising alternatives to analytical methods because they're universal function approximators. They model complex input-output relationships better than analytical methods and can approximate multi-model error sources like multipath and NLOS in GNSS measurements. However, they require large quantities of labeled data to learn the input-output mapping for their tasks like classification or curve fitting. Additionally, using DNNs for GNSS positioning is challenging because they have set valued inputs, which vary in number and order over time, which common DNNs cannot handle. The GNSS inputs are also poorly conditioned. Satellite ECF coordinates vary from minus 20,200 to plus 20,200 kilometers in all three ECF coordinates, whereas satellite pseudo-range measurements, while of the same magnitude, have significant variations of about 100 meters. Since these values are not similarly scaled, common DNNs cannot perform as well. Finally, datasets might be geographically limited or might not have widely available ground truth. In our work, we overcome these challenges to design a deep neural network for the positioning domain. We estimate position corrections to a supplied reference position, use well-conditioned input features and output for scaling and global applicability, develop a geometry-based data augmentation method to prevent overfitting, and validate our proposed approach on real-world data. In our validation, we saw that the performance depends on the magnitude of randomness in the initial guess, with smaller magnitude resulting in smaller errors, and the network learning the magnitude of the largest corrections. In all networks we tested, we saw the networks outperform WLS in the vertical direction. Thank you. Please check out our paper in the winter 2022 issue of Navigation, and our code is publicly available on our lab's GitHub webpage.